The chain rule. I can find the derivative of functions that have the format f of g of x, which means g of x is inside the function or substituted into the function f. All right, so we've so far learned how to take the derivatives of functions with the power rule, the product rule, and the quotient rule. Now, we're going to learn about something called the chain rule. All these rules are actually just shortcuts used rather than using the formal definition of the derivative, the limit as h approaches 0 of f of x plus h minus f of x all over h. Or there was the other way that we've used, which is the limit as x approaches a of f of x minus f of a all over x minus a. When you would do those long calculations, take the limit, cancel out some terms, and find the derivative. So these again are just as a reminder, they're all shortcuts rather than using the formal definition of the limit. The formal definition of the limit is something that we should know how to use. We use the chain rule to find derivatives of functions composed with other functions. And what I mean by that is, in other words, when we have an inside function and an outside function. So when you see that you have an inside function and an outside function, you know that you will be using chain rule, which is, I believe, nearly one of the last of the rules of taking derivatives. All right, so how do we use chain rule? The chain rule says if you have a function that looks like this, f of x is equal to h of g of x, a composition of functions, then here is the derivative. Take the derivative of the outer function h while keeping the inner function the same times the derivative of the inner function. This is how the chain rule will work out. In other words, I also added this if, some people are not comfortable with this notation. But in other words, it means if you have an outside function with an inside function, then the derivative is going to be the derivative, this little prime notation, the derivative of the outer function while keeping the inner one the same, times the derivative of that inner function. So this and this are the same thing. This is just rewritten in case this notation is confusing for you. All right, let's go ahead and jump into some examples. All right, let us take a look at this. And for these examples, I have color-coded the examples just so that you can easily see what is my inner and what is my outer function, so you can see how I am applying the chain rule. All right, so find the derivative of f of x equals 2 to the x minus 5 to the 10th power. All right, so here's one thing I want you to keep in mind. You can, if you want, use product rule here. But you know what? You would have to rewrite this 10 times and take the product rule like about, 5 or so times. And it's going to be a very, very long problem. Or you could write this whole thing out 10 times, do FOIL about 10 times, and then take the derivative using the power rule. But again, that's going to take a very long time. The shortest way to do this problem is to use chain rule. Because my inner function is 2x minus 5, my outer function here in red, it's x to the 10th power. If we imagine that this right here was an x, it's going to be x to the 10th as my outer function. Let's go ahead and see how we would do this. All right, here's a reminder of my rule. What I'm going to do to take the derivative of this is I'll take the derivative of my outer function, which is the x to the 10th. I'm going to keep the inside the same, which is 2x minus 5. Then I'm going to multiply by the derivative of that inner function, and the derivative of just this green part will be 2. Let's go ahead and see how this all comes together. So here I rewrote my problem. Now I took the derivative of the outer function right now. So hold on, I'm still not done with applying the rule. You'll see in a sec, but right now let me pause here. I brought the 10 down, and then I subtracted 10 by 1 to get 9. See how I just took the derivative of the red part while keeping the inner function the same? Right here, I'm doing this part. So I took the derivative of the outer part and I kept the inner function the same. Then the rule says I have to multiply by the derivative of the inner function. Well, the derivative of my inner function, what is the derivative of 2x minus 5? It's just going to be times 2. Now I have applied my rule. Basically, this is your derivative, but you want to go ahead and simplify what you can. So 10 times 2, guys, is just going to be 20. And then to the ninth power, obviously I'm not going to expect you to FOIL this out 9 times. Just leave it like that. This is your derivative. This is it. That's your answer. So that's example 1. These examples will kind of move up in difficulty. Let's take a look at some more. All right, this one's actually very similar to the last scenario. So our inner function, so again, I know I have to use chain rule because I have an inner function and I have an outer function. So I have this function that's raised to the 4th power. So basically, I have that inner and outer thing going on here, especially if you see parentheses. That's also a key there to use chain rule. Here's my chain rule, just a reminder. I'm going to be taking the derivative of the outer function. So I'm going to bring down the 4, subtract by 1, keep the inner the same, which is this first part. Then I'll be taking the derivative of that inner part, which is going to just be 6x. Let's take a look. All right, here we go. I took the derivative of my outer function. I brought down the 4, I subtracted the 4 by 1 to get 3, and I kept my inner function the same. So I just did this first part of chain rule. But I'm not done. It says I have to multiply by the derivative of the inner function, which is 6x. Next, what you want to do is simplify this. 4 times 6x is going to give you 24x. And you are done. That is your derivative, and that is it. You do not have to FOIL out the 3x squared minus 5. You don't have to do that 3 times. Absolutely not. This is your fully simplified form. We could go ahead and, circle your answer. And again, feel free to pause the video if I am going too fast, because I know I am. But anyways, example 3. Find the derivative of this function. Again, this is similar to what we've been working with, but again, I'm just reiterating this as practice so that you can get used to using this chain rule. Example 4 and 5, I believe, and 6. So later on, we're going to see some more examples that involve some trig, so be aware of that. All right, so again, I'm going to be applying my chain rule. I'm going to take the derivative of my outer function while keeping the inner function the same. Then I'm going to multiply by the derivative of my inner function. The derivative of my inner function in this scenario, it's going to be negative 9x squared minus 3. That whole enchilada. All right, so now we're going to think about, okay, now we got to simplify. So we're going to do 6 times negative 9x squared minus 3. Basically, if I want to multiply 6 by this quantity, the 6 must distribute in here. Or you could rearrange this, right? I would just go ahead and multiply, but I also added in this extra step, if you need it, that you can rearrange this as in moving these two, swapping the positions of these two so that you can see clearly that I'll be distributing the 6. Let's go ahead and do that. Great. So you get negative 63x squared minus 18 times negative 3x to the third minus 3x to the 5th power. And I believe that's it. You do not have to simplify this anymore. You circle this. This is your answer. Great. A problem with the square root. Awesome. All right, so I see I have the square root of x squared plus 1. So again, our usual technique of trying to rewrite this using power rule is not going to work because there's a plus 1 in here. We can't distribute the 1/2 power in there because there's a plus in between these two. So that's why I can't use my power rule shortcut that I usually do with square roots. This is actually going to be a chain rule problem. All right, so my inner function is going to be x squared plus 1. My outer function, that square root part, let's see what it is. Boom. The outer function is x to the 1/2 power. That's to the 1/2 power. So rewrite that small. I know it looks big, but that's the best I could do here with exponents. All right, so my inner function is x squared plus 1, and then my outer function is going to be x to the 1/2. So let's go ahead and start taking the derivative. I'm going to take the derivative of my outer function while keeping the inner the same. Here is that step. I brought down the 1/2. 1 half minus 1 is negative 1 half, and I kept my inner function the same. Next, I'm going to multiply by the derivative of the green part, which is just 2x. Okay, I don't know why that's not popping up. Where is 2x, guys? Okay, it's not showing up. It should show up, so let's see. There it is. Okay, so let's just disregard these right here, okay? Right now I'm on this step. For some reason my animation times 2x popped up right now, so ignore this. I'll talk about this right now. Alright, so this right here is my derivative. I took the derivative of my outer function. I multiplied by the derivative of the green part, which is 2x. Now, the simplification part comes by 1 half times 2x. The 2's just cancel, and you're left over with x. Great, so then I have x times x squared plus 1 to the negative 1 half. Now you remember how I am pushing you to rewrite negative exponents into positive exponents, and you do that by rewriting them by pushing them into the denominator position or the numerator position. In this scenario, because it's a negative 1 half and it's on the top, to rewrite this, I'm going to move it down into the denominator position. And then we all know that to the 1 half power means the square root. So you definitely want to rewrite this to the square root at the bottom right here. So this is going to be x. This stays on top because there is no negative exponent to it. This is right here on top. This part in the parentheses got moved down because the exponent was negative. And then positive 1 half, the exponent became the square root. I just rewrote that as a square root. Do raise your hand at this moment if you want some clarity on how I went from this step to this step, so I can help you out there. Otherwise, let's go ahead and move on to the next examples. We got 2 more. Alright, let's go ahead and talk about some trig functions with chain rule. So, I want to just mention that trig functions with chain rule ends up being confusing every single year. Alright, because right here, if we take a look at this, some students think this means cosine of x times 3x, and then they try to use product rule. That is very incorrect. This is cosine of 3x, right? Because this is not cosine times 3x because there's no x after the cos, right? Cos by itself doesn't mean anything. So this is cosine of 3x, where my inner function, instead of x here, you see 3x. So my inner function is 3x. This is going to be a chain rule problem, therefore. All right, let's go ahead and begin. So this is my rule. I'm going to take the derivative of my outer function while keeping the inner the same. Then I'm going to take the derivative of the inner function. So the derivative of my outer function, the derivative of cosine, is sine. Or negative sine, I believe. Yes, negative sine, right? And I kept the inside the same. See how I took the derivative of the red part, but I kept the inner part the same. Then I'm going to multiply by the derivative of my inner part. The derivative of 3x is just 3. Let's go ahead and rearrange this, and you are now done. This is your derivative. You want to go ahead and circle that. That's your answer. All right, let's move on lastly to example 6. What if I told you to find the derivative of sine to the third power of x? All right, so here's again a reminder of my rule. I want you all to remember, and that should be a 2. I'm sorry, 1 second. I want you all to remember that sine to the third of x means sine of x to the third power. It means I'm taking, I'm doing 3 sines multiplied with each other, right? So therefore, if you were to rewrite it like this, you can clearly see that you have an inner and outer function going. For some reason, though, I wrote, I kind of reversed my colors that I've been doing, but yep, let's try to work with it. So my inner function right now is red, my outer is green, which is kind of opposite, but let's work with it. All right, so let's go ahead and take the derivative of the outer function, which is in this scenario going to be in green. I brought down the 3, and I subtracted 3 by 1 to get 2 there. And then I multiply by the derivative of my inner function. The derivative of sine is cosine. This is me using chain rule. See, I took the derivative of my outer function, keeping the inner the same, multiplied by the derivative of my inner function. The derivative of sine is cosine. That's all I did right now. All right, so, I don't think I see anything else I can simplify. Let's go ahead and drop the parentheses and rewrite this properly. There we go, that's it. That is your answer for this scenario. So you notice how I put this squared back in before the x. That's just how we write exponents with trig functions. And then I just multiplied the cosine x and I put the 3 there. This is your answer. You could just circle it. Again, I apologize for the mismatch in colors here. I tried to keep the inner function green, the outer one red. Be aware that in example 6, I just switched the colors around, but it's still the same process that I did with chain rule. All right, here's to hoping that we've met our learning target. We're going to move on to the task, and let's see you get this into practice.